Good afternoon, everyone. I'm John Ellis, and welcome to the Compealing Code Chemistry, which I think is the third in the series on Compealing Code and part of the first series that we've been running over the last few years. A little about Paul. Paul's president of the institution and wealth of experience. So what I'll ask is I'll hand over to Paul and let him get in. The structure will be Paul will do his presentation. There'll be time for a Q&A afterwards, and then we'll sort of follow up on the end of it. Okay, I will mute myself and hand over to Paul.
Lovely. Thank you, John, for your kind words. Good afternoon, everyone, on this lovely, well, where I'm sitting, sunny afternoon. Welcome to this webinar from the Institution of Analysts and Programmers. The goal of the IAP is to improve software for society. My name is Paul Linham. I'm a fellow and the president of the IAP. And hopefully this afternoon, I'm going to entertain you with a little bit on software quality called Compealing Code Chemistry. So just to give you an overview of what I'll be covering. So first of all, I'll do a review on what compealing code is. Then we'll look at how we can assess code against compealing code. We'll go through a very simple example, and then I'll go through the refactoring steps that is used in the example, and then we'll just summarize, and after that you'll have an opportunity to ask questions. Okay, so what is compealing code? Well, to look at that, we need to look at the abilities of code, and this is a sort of a traditional perspective on code. So we have a triangle or a pyramid with ascending abilities. So at the bottom we've got legibility, which is fairly straightforward. As long as your editor has got a contrast between the font and the background, you should be able to read the characters on your screen. The next level is readability, and this is the ease of which a reader can understand the written text. So if you're looking at some source code from a particular language, you should be able to pick out the keywords, work out what's an identifier. You can pick out things like sequence, selection, this is an if, or this is a switch or a case, an iteration, or this is a for, this is a while or a repeat. So that's that sort of level. And if we go up to the next level, we come up to the understandability. And this is the ability for you to fully understand the code. It's what I call comprehensible. And obviously there'll be different levels of that. Sometimes you'll look at it and it'll be quite easy to understand, and in other cases you might have to look a bit harder, and then you'll eventually understand. So there are degrees of understandability and the time it takes to reach that level. However, just because you can understand code, that's not the end of the story. So the next step up is believability, and that is to have the confidence in that this code will be reliable, its behavior will be acceptable, whatever you throw at it. And that's most probably the hardest level in this model to attain. Now, what I want to show you is my idea of how you should look at code, and this is just my humble opinion that I came to after many, many years of looking at code and deciding what was important, and also the idea that you don't have to rise up a pyramid, that some of these exist and they coexist as well. So the three things are comprehensible, which is your understandability, your appealing attribute, which is that the code is well designed, that it's got good structure, and it's easy, again, it's easy to read, and then compelling, which is the bit about whether you're confident that when this code runs, it'll do what it's supposed to do. So looking at the comprehensible part of it, again, as I said, with the other model, you'll have different levels of comprehensibility. But that should be, one of your goals is to get this code as readable as possible, and you'd like it to be as readable as English prose. So what it reads off as if you're reading a passage in a newspaper, whatever. You understand it. Now the appealing part is a bit more difficult, but it's as some people have said, I'll know it when I see it. And just because you've written something that's understandable doesn't mean that it's particularly well designed. So you could have a big ball of mud, or you could have God classes, or you could have, instead of it being layered, you could have it all mixed up. And for some of you who perhaps were coding in the 90s, you might remember the RAD paradigm, which was rapid application development, where you could get a tool where you could visually design the software. So you could drop on a form, and you could drop on some user interface components. You might be able to drop on some business logic components, and then you'll have a data source, and you'd connect it up via the properties in the object inspector, and you could do this with very little code. You might have to put a bit of logic in there, but then you'd run it. It would seem to work incredibly fast. And for small applications, that was a great way of producing applications. But the problem is that you've got all your user interface, your business logic, and your data persistence all in the same file. And as systems get bigger, you want to be able to sort of differentiate them. So you'd have a layer, user interface layer. Traditionally, you may have several other layers, but business logic is quite often one, and then a data persistent layer. And the good thing about it is if something goes wrong, you can isolate it. If you've got loose coupling, you can, if you need to swap out, say, the back end, so I'm going to change my data persistence, then you're only concerned with the data persistence layer. So, having good code, readable code is one thing, but having good design is also another important thing, and good structure. And then the last thing, you've got to be able to trust this software. I mean, if you use the banking application and you take out 20 quid, but it's taken out £100, you wouldn't be very, very happy, would you? So you've got to have trust in the software that you are producing. And that sometimes can be very hard to do. But what you've got to be able to do is to, if you do get an error, is if you can handle it, great. If you can't, you need to handle it gracefully and let the user and the developer know somehow. Now, where all these three attributes meet, you've got a sweet spot in the middle. And this is where I say you have compealing code, because it's a portmanteau of comprehensible, appealing, and compelling. So that's where you get your compealing from. So compealing code is easy to understand, it's well structured, and is compelling, i.e. you are persuaded of its behavior when it runs. So how can we use this concept to assess code? Well, what I've done is I've created like a little periodic table, hence the chemistry. So we've got the three attributes of compealing code. We've got comprehensible in blue, appealing in yellow, and compelling in red. We've got a little chemical symbol for each one. And so that's C, that's not cerium, that is comprehensible. A for appealing and CG for compelling. And then when we look at the code and we look at each of these attributes, we'll decide whether it's compliant with a tick, it's non-compliant with a cross, and if we're undecided, we'll use a question mark. So what we'll do, we will just bear in mind this little table, and I'll have it on the screen so we can just remind ourselves what we're talking about. So to start off with, I've got a small snippet of code. As you can see, it's a function. This function's called A, and it returns a double, and it takes two parameters, X and Y, and then it returns the product of those two parameters. Now, at this point, we look at this and we can understand some of it, but we can't understand all of it. For example, what do the identifiers A, X, and Y represent? In what context would you use it? So we only have a partial understanding. So what I've done there is I've marked comprehensible as a question mark, but it's certainly not appealing, and it's certainly not compelling. So yeah, what do these identifiers represent? And could we inline this function without losing anything? So if you see on the bottom left, I've inlined it. So this is what you would see if you put it in your code, took it out of the function, put it in your code. You've got the result is assigned to the product of X and Y. And that's, okay, you don't know what X and Y are, but you know exactly what it does. Now, if you look at the function call on the right, you've got more of a problem. For a start, you don't know what this function A does. You don't know what it means, and you'd be compelled to go off and have a look at the implementation for function A to see what it does. So in fact, it's less readable than inlining it, and that's something you don't want to do. You don't want to say I want to inline functions. I mean, there is cases where you do want to inline functions, but the compiler should do that for you. If you're looking for speed increases or things like that, you don't do it yourself. You'll ask the compiler to do it. And inlining is can be quite useful if you've got quite a complicated algorithm, even if it's just a one-liner. If you replace that with a well-named one-line, if you well-named method name, it can make the code a lot more readable, and also, if you think about it, you're also centralizing it in one place. And if you want to change the algorithm, it's just changing one line. So we've got some problems with this code. So the next step along, what's happened is that this function has been renamed to area, and the two parameters, L and W, the implementation is still the same. It's L times W returns that. So looking at this now, I think we can guess what's happening here. We've got an area, and it's taken two parameters. Could this be length and width? And when you multiply length and width, you get the area. Yes, you get the area for a rectangle. So now this has become more understandable. As long as we we go along with these assumptions. And so what I've done for the time being, I've marked this as it's comprehensible. It's certainly not appealing. And again, we certainly couldn't rely upon this code. So step 3, in fact, what's happened in this case is we've renamed the function's name using a verb-noun combination. So it says calculate rectangle area. So this actually tells us what it's doing. It's calculating the rectangle's area. It's as plain as day. So there's no confusion there. That's quite explicit. We've renamed the parameters to length and width. And again, the implementation is the same, return the length times the width. So looking at this, it's both now comprehensible and on a very superficial level, it's appealing because the intent is explicit. But again, it's not compelling in any way. So some more refactoring here. Now, what we've done, we are talking about a rectangle. And if you think about it, a rectangle has to have a width and it has to have a length. I mean, if it didn't have a length, it would just be a line, wouldn't it? So it wouldn't be a rectangle. And if it didn't have a length and a width, it'd be a point. So it's not a rectangle. So if you think about it, it's got to have a length, it's got to have a width, and they've got to be greater than 0. Otherwise, you wouldn't have an area of a rectangle. So what this does, it checks that both the length and the width are greater than 0. And if that is the case, it will return the length times the width, which is the area of a rectangle. However, if either the length or the width or both does not comply with those constraints, then it throws an exception. Now, in this case, it's been fine-tuned to an argument exception, because depending on what language and what libraries you're using, you can actually fine-tune the exception to a type of exception. So rather than a generic exception, we've thrown an argument exception, because one of the arguments or both of the arguments have not complied with our idea of what the constraints are. So what it'll throw an exception saying dimensions must be greater than 0, and then print out the dimensions that were passed. So we've got an idea of what went wrong. Now, looking at this code, we can now say to it, yes, there's been some defensive programming used here. We are guarding against the inputs that we are using in our calculation. And yes, this now is compelling. So we've got it comprehensible, appealing, and compelling. But this is not the end of the story. Now, instead of this being a standalone function, say now it's part of a class, a polymorphic class such as shape. And then what we could do is we could inherit, say, a rectangle or a circle or an ellipse. And in that case, area would be a method that would be used with all of those. And area would be good enough because we know that it's being called on a particular shape, such as rectangle. So in this example, we've got tile cover is assigned the rectangle area. Now, you may wonder where the parameters are, because it's not using any parameters. And the reason for this is because if we've gone into the class now, we can say, right, those parameters that were being used can now become attributes or properties of that class. And we can set those separately. So we could then assign the length and the width of those rectangles. And this has got some good benefits, because when you read the signature of a method, if it hasn't got any parameters, you can read it much quicker, especially if it's a well-named method. The brain doesn't have to look at the parameters, go through every parameter, work out what it's supposed to represent, its type, any constraints it has, and so on. So by minimizing the amount of information in the method, and remember, the average human brain can keep 7 plus or minus 2 items in short-term memory at any one time. You can make it much easier to get the concept of the method and keep it in memory without having to repeatedly reread it. So this makes the reading process much slicker. Now then, if you think about it, because those attributes or properties within the class are going to be used in other functions. For example, besides area, we could have a perimeter method, and they're going to use the same attributes which were previously our parameters. Rather than each method within the class have to do the check-in, the defensive programming, every single routine or method, wouldn't it be better where you could centralize it? So in this case, what we've done, and I've done this with length, but we would do the same with width. We've just got a private field called length with lowercase l, and then we've got a property called length with uppercase L. And if you want to get the value of length, it just returns the private field. If you want to set it, then it does the check in there. It checks the constraint. So if the value is less than or equal to 0, we'll throw an argument exception, length must be greater than 0. Otherwise, it'll accept the new value. So what we've done now is that we've centralized the check-in in one place, and we've left those methods free of all this check-in and makes them much less complicated. So we can go back to our implementation for it. You can see that it's gone back to just returning the product of the length and the width, while it still remains comprehensible, appealing, and compelling. So just to summarize what we've done, we've renamed a method so everyone can recognize what it does. Now, this might seem trivial, but I think it's a very important point. When you write code, yes, you're writing it for a particular machine, to run on a particular machine, but really the audience should be another developer. The machine can understand very succinct, terse code that when a human looks at it, it takes a long time for them to comprehend what's happening. So you don't want to write it like that. You don't want to write it as in the old days of the C golf type of thing, where you wanted to get as much functionality in the least amount of lines as possible. We don't have the problems of memory constraints anymore. So the idea is to make this as readable to a human being as possible. So the method should scream out exactly what it's doing. Similarly, with the parameters, we've got to rename those to convey their use. We added some contract or defensive programming to it, and I'll talk a little bit about contract programming a little bit later. And if this is part of a class, then we can refactor it, for example, making the parameters properties. And then lastly, what we did was we moved the defensive programming away from the routines or the methods into the property setters. Okay, so let's just have a look at some of these quick points. So this example covered a very simple, I'd say even trivial example of what can happen with code. And the appealing attribute is usually assessed against code structure. Obviously in the small example we had, it's more difficult. But if I had a much more real life one, we'd most probably be here for hours. But you can just imagine that now that you're appealing, you'll be looking at the design of the code. You'll be looking at things like loose coupling, that it's got single responsibility. In fact, all the solid, if you think of all the solid things, you'll be looking for that. Naming, well, that is you as the programmer's opportunity to make this clear, to explain your intent. So the language you're using doesn't enforce this. It's your responsibility as the author to do this. And if you don't exploit it, then you're missing an opportunity. And you may have used this, you heard this many times before. Code is read many more times than it's written. So you've always got to bear this in mind. It might take you a little bit longer to write it, but it'll save a massive amount of time in the future when one person and another reads it down the line. So the more readable it is, the more time is saved, and also most probably there's less chance of something going wrong or bugs being introduced because people have not realized the proper intent. You want to avoid duplicate code. So rather than, with our example, we did the check-in of the parameters. We don't want to do that in every single routine that uses those parameters. So we centralized it. So what we've done there is we've kept the code dry, which stands for don't repeat yourself. So you don't want to see the same 3 or 4 lines all over your code. Otherwise it becomes wet. You write everything twice or thrice and so on. So if you see that in your code, that should be telling you, I need to be able to put that into a method somewhere. And when you look at a method, you don't want to see lots of levels of branching. You want to keep it quite simple. Keep a minimum number of levels. Short, sweet, and simpler makes it easy to comprehend. So if you have to go down, say, 3 levels of iteration or 3 levels of selection, then think about starting at the inner level and making that a well-named method. And when you step up to the next level, that will call that method, but that will then be called by the first level. So you're just making things easier. So when you see the top level one, you'll see, wow, that's very simple. It's doing this. And as you step down, you'll get more information about what's happening at each level. You want to avoid complexity, and it's not always easy to do, I admit. Keeping your code attractive and easy to understand, so readers of your code find it transparent. And this often comes with experience. There's a bit of a swings and roundabouts. If you've got something that's terse, you may want to expand it out into several lines. So in one way, you're increasing the amount of code, which you don't want to do, but on the other hand, you're making it simpler. But I think simple is more important in many instances than keeping it succinct. It's nice to do both, but can't always be done. And then make the code compelling. Use contracts or defensive programming. Some people use things called offensive programming to get it done. But I mean, some languages have have abilities. They have keywords for contract programming, such as Eiffel. They've got keywords like require and ensure and so on. So you can look at preconditions and then post conditions. So the idea with the contract program is, as long as your preconditions are met, I will guarantee that these post conditions are met. Now, for languages that don't have those in built facilities, most languages have can use the assert statement. It may not come with the language, but you'll get a library that you can use it, and then you can use assert to do your preconditions and your post conditions. But you have to be very careful how you use an assert statement. I've seen an assert statement contain a call to open a database connection, which is fine. While the assert statement is working, it'll return, the open will return a Boolean to say, yes, I've opened a connection to a database, and the assert statement will say assert true or whatever that this has happened. The problem comes is when you decide you want to produce your production code and you turn off asserts, it's now turned off the connection to the database. So in this situation, what you do is use a variable to get the result of the connection to the database, and then do the assert on your variable. So you have to be very careful how you use asserts, and that is an example of a recoverable and a non-recoverable error. So a recoverable error would be, for example, if you try to open a database or try to say get access to a network connection, the internet or whatever, and it was down, then you can most probably retry and you can recover from that at some point. But in that case, with the open database connection had been taken out by the compiler, that's a non-recoverable error, and it doesn't matter what happens, you're never going to be able to recover from that one. So to sum up, compealing code is a powerful concept. You can see how using these three aspects of source code, comprehensible, appealing, and compelling, can be used to produce higher quality software. And if you use it in a check-in process, then it can produce software which is easy to understand, is well structured and pleasing to read, and it persuades the reader that the code will behave as intended when it runs. And this has the benefits that the software can be easily maintained, and this is becoming much more important with these days with lots of frequent and shorter release cycles. It's important that you can maintain software very easy. And lastly, it will hopefully lead to more reliable and trustworthy software, which hopefully we all would like to do. So I hope I haven't bored you too much with this presentation, and I am now open for questions.